Okay, so it's you, me, physics, calculus, and Fortnite. So we're gonna look at this hypothetical scenario. Jones is on a tower tilted where he shoots at any player with a grenade launcher. Length of the grenade launcher to the ground is h, and its launcher v naught. What is the distance between the building and the player if the grenade launcher hits? Assume no air resistance. Okay, this is the standard kinematic type problem in physics. We're gonna solve this using kinematic equations. So, and we're gonna break up its components into horizontal and vertical. Therefore, since there is no air resistance, horizontally, velocity is unchanged. Therefore, its position function can be modeled as since v naught is not changing. And for the y direction, it's going to be modeled as since we're assuming that the downward direction is positive, it'll be minus h and g will be positive. Okay, so now we can find that the common variable between the two is t, and we also want y to be 0. So we can set that equal to 0, solve for t, and plug it back into x. So let's do that. I'm going to add h on both sides. Multiply both sides by 2 and divide both sides by g. So take the square root on both sides. So now that's our time. Plug this into this. And there's your answer. After winning, Jonesy T-poses and spins with an initial angular velocity omega naught. And then with a rotational inertia, 7/12 ml squared. He pulls his arms in later on and reduces his inertia to 1/12 ml squared, sorry. Assume his height is, mass and height is m and l. We highlight all the important, underline all this important stuff. What is the work done by Jonesy? Okay, to tackle this, I'm going to use the work energy conservation theorem. So that's work is change in energy in a given system. And we have to find rotational kinetic energy. We need to find its rotational inertia and its angular velocity. We know the first angular velocity and its rotational inertia. We do not, however, know its second angular velocity, but we do know its second rotational inertia. To find the second angular velocity, I'm going to use the fact that its angular momentum is going to be conserved in this situation. So I'm going to say Li has to equal Lf. That means II omega I has to equal IF omega F. We know II and IF, those are those things. So and omega I is just omega naught. So we're going to write that down. Omega naught has to equal 1/12 ml squared omega f. We want to solve for omega f. We can cancel ml squareds out, multiply 12s on both sides, so these two go away. And we're going to get 7 omega naught has to equal omega f. Okay, now we're going to bring this here. Change in energy is the same thing as final energy minus initial energy. So the work has to equal energy final minus energy initial. Okay, energy final is just I omega I squared. So it's going to be, no, energy final is this one, my bad. So that's going to be 1/12 times ml squared times 7 omega naught squared minus this inertia, which is 112, this inertia, getting confused, sorry, 7/12 ml squared omega naught squared. Okay, this looks like it's gonna be 0, but it isn't. Why? Because this 7 is gonna be squared too. This is gonna turn into 49 twelfths. Okay, so we're gonna have W equals 49 twelfths ml squared omega naught squared. Remember to square the omega naught too. Minus 7/12 ml squared omega naught squared. Combine like terms because these three variables are in the same exponentiated and order and the same variable essentially. Work would have to equal 49 twelfths minus 7 twelfths is 42 twelfths ml squared omega naught squared. Jones's grenade explodes in a perfect sphere and its radius increases at a constant 3 meters per second. It will dissipate when its volume is 1372 thirds times pi. What is the rate of change of volume at that instant? Okay, this is the calc section of our FRQ, and this is looking like a related rates problem. So what I'm going to do before I do anything is I want to know the radius when that volume is that number. So I'm going to set the volume equal to the 4/3 pi r cube and solve for radius. So this is how it's going to look like. 1372 pi over 3 has to equal 4/3 pi r cubed. Okay, multiply 3's on both sides, and you end up going to cancel these two out. Pi is going to go away too. So we're going to divide 1/4 on both sides and then cube root it. I'm going to use my powers and say this is 343. Don't trust me? Put it in a calculator. Has to equal r cubed. This is obviously a really famous perfect cube, and this r would have to equal 8. So now that we know the radius is 8, we're looking at the rate of change of volume. So time to take the derivative of this thing. Okay, derivative of the volume is dv dt. Right? This 4/3 pi is a constant. R cubed is not. So that is going to be power rule. Going to bring the 3 to the front, right? And we're going to subtract 1. So this 3 times 1/3 goes away. So we're going to get 4 pi r squared. Okay. We know 8 can go into radius. Oh, sorry. I made a bad mistake. Been doing implicitly. dr dt needs to remember. Don't know what I did. Okay. So now that we know also that dr dt is 3, because its radius is increasing at a constant 3 meters per second, right? We know dr dt, we know 8, we want dv dt. We can just plug and solve. So this would have to be equal to 4 pi 8 squared, and then dr dt is 3. I'm going to use my math skills, aka the answer in my hand, and say this is 768 pi. Would have to equal the rate of change of the volume at that moment. When the dissipation starts, the rate of change of the radius can be modeled as r of t equals sine of x over x. As time goes on, what will the volume of the sphere approach? And I just realized I put that in parameter. Anyways, the point is, when time goes on forever, what will the volume of the sphere approach? Because this r of t would it would fluctuate, never really become 0, and continues to stay 0, kind of. So since r of t is a rate, this is me thinking of integrals. Okay. And so we want to find volume, we can find the radius when it goes on forever, and then find its volume by using the sphere equation. And we can use the dissipate radius, right? And then find the integral of the entire thing, and then add that to find your actual thing, to find your actual total radius. So this is going to be the starting one, 8, plus integral from time equals 0, because that's when dissipation starts, to infinity, because we're looking when time goes on forever, of sine x over x dx. And this famous integral is actually converges really nicely to pi over 2. And if you want me to work that out, well, we can do that next video. So our radius would have to equal 8 plus pi over 2. Okay, this is radius. We want volume. So we know that volume would have to equal 4/3 pi times the radius, which is 8 plus pi over 2. 8 plus pi over 2 cubed. Now, I'm not going to simplify this. You usually can have calculators. So I'm just going to have the answer on the board or like on the video, and you can probably like write that down. So I'm just going to leave this right now as this.